Alright, good. Cool. So then today we're going to go through some of the homework questions. So the 3 homework questions that were posted from the 3 different presentations. So one was to derive the following expression for the inverse map. Another was to come up with a way to do interpolation of transformations. And then the final one was to read about Borg and sort of matching and descriptors. So we'll start off with these first 2. So did anyone do this question? Yeah, do you want to go onto the board?
Oh boy.
And write out your solution?
What if it's not right?
Oh, well, I mean, I have the answer, so I'll know if it's wrong. And then explain each step as you go.
Okay.
Is there anyone I can see with that too?
Yes.
Yep.
You might move my laptop a bit. Can you see the board okay?
I can, yeah.
Okay. Okay, so the problem is, my writing's also not the best. I apologize in advance if you eat. UD5 of my inverse, right? So what I decided to do was, much like the other derivative maps that we took last week, write it out in your core differential form. That's not the right word for that. So I take the limit as epsilon goes to 0 of, now taking the mapping, so that's phi box plus
Yep.
and so then from here we can start to apply some of the nice important expressions that we know. So the first one that I decided to do was to actually just evaluate the box plus that's in here. So that then becomes limit as epsilon goes to 0 of EI epsilon phi inverse, and then box minus phi inverse again, all over epsilon. And then the next step that I did was to expand out this inverse term.
Okay.
So then, again, limit, this became phi inverse, because as we know for an inverse, for 2 terms, we can swap them and take the inverse of each of them.
Yep.
So we have phi inverse, then we take the exponential map of EI epsilon, and that is inverse. And again, box minus phi inverse over epsilon. And then we can use the inverse identity, and we can replace this second term here with the exponential map of the negative of the term being evaluated. So then this becomes phi inverse again, minus EI epsilon. And then box minus phi inverse over epsilon again. And now at this point, I decided to actually evaluate the box minus operator. So as we know, we can write that out as log of the first term, which is then phi inverse x minus EI epsilon times the inverse of the second term, which then becomes just phi all over epsilon. And this interior here is the adjoint related identity.
Yep.
So then I'm going to continue over here now, which then becomes the limit as epsilon goes to 0 of log of the exponential map of phi times negative EI epsilon over epsilon. Your log and your exponential cancel. The epsilon and the epsilons cancel, and then you're left with negative EI times phi. Or is it phi times EI?
Yeah, there was. Wait, why would there shouldn't be phi inverse? Because when you do so see in the adjoint related,
Yeah.
see that so in the normal one you have the first term
Oh,
is
the
phi,
first term is
but
phi,
here your
okay.
first term is phi inverse.
Okay, so then
So that should be minus phi inverse times EI.
I see.
Yeah,
That's
yeah,
minus
here's
one.
one. Yep.
And there it is.
Yep, minus phi inverse times EI.
Okay.
And then just to
Anything else?
yep, no, that's it.
Okay.
Alright, yeah, that's really good. Alright, Nav nailed it. Good job, Nav. So just the basic, so Nav went through all the steps, which was really good. But just to give basically the overview of what they presented in the paper. So exactly what Nav went through, right? So the first step, we applied our standard rule of our differential identity. Then we expand out what the box plus and box minus operators actually do. Then, so from this step to this step, we basically are applying that adjoint related identity, but for phi inverse. And then the log and the exp cancels out, and then we have that because we're doing the rotation of this quantity here. The rotation is basically, the mapping is linear, so then you can pull out the minus, and you can pull out the epsilon, and they'll cancel out. And then you end up with what Nav had previously, which is minus phi inverse times EI, which you can then write out as basically minus the rotation matrix, so the rotation matrix transpose times EI. So then for each basis vector, you just end up with this expression back here, which is just the minus of the rotation matrix.
So I just have a question.
Does it matter that the first line has the order different on the composition?
Sorry, the first line has the order different.
So you have, so Nav has X, EI. Does he then, and then followed by the, large, what is that, theta?
The large phi.
Yeah, I followed the
Phi.
box plus.
Sorry, which?
So you have log.
Nav's line number 2 doesn't match your line number 2.
Oh yeah, no. So the line number 2 there is because, so this is after you apply all the inverses. Right?
Oh, his line number 2 is my
Yes.
line number 5.
Yeah, it's like, so it's skipping a bunch of the intermediate steps.
Okay.
Yeah, exactly. So Nav did a great job of going through all of each step line by line. So this is kind of the condensed version. Yep.
Just have a question. So phi is a mapping from SO3 to R3, right?
Phi is the group element. So yeah.
Yeah, but I mean it's from SO3 in this to R3, right?
So technically what phi would do if you look at the mapping is it's from R3 to R3 actually. Because you'd be taking a vector in R3 and you can use phi to rotate it into another element of R3. But phi itself is a member of SO3.
Can you go back to the previous slide?
Yep.
Sorry, no, that's geez. Yeah, I had in mind the box minus.
Oh, okay.
Box minus, right? I mean, it takes
Yeah.
to SO3
Yep.
and yeah, it goes to R3.
Goes to R3. So
That's
it's
right.
basically like a difference of rotations.
That's right.
Yeah.
And can you go back?
Go forward one. Yep.
So, okay, and so phi will be mapping from again?
So phi by itself, so if you're looking at the coordinate mapping,
Yep.
so phi is basically, you can think of it as a rotation matrix, right? So phi is a mapping from R3 to R3.
Oh, I see. Oh, okay, so we the main cell, okay, I'm just checking the types,
Yeah.
okay, so, that's right, okay,
Yep.
that makes sense.
Yeah, I think part of the problem is you kind of call it a rotational matrix when you're talking informally,
Yeah,
but it's not.
Yeah, it's a group element. Yep.
Rotation matrix, like isn't SO3 defined as all rotation matrices?
Yeah, exactly.
So it's rotation matrix.
It is a rotation matrix, but so if you look at the paper, their definition is a little bit stranger. So it's not stranger, it's still correct. They're just saying that So capital phi is an element of the group, so it's an element of SO3. But then when you apply the C operator to it, or the C function, it extracts the rotation matrix from the group element.
In the paper, they define phi as not, like it can be any
rotation, parametrization.
Yeah, so any parameterization, yeah. So
taking a C actually makes it everybody.
yeah, so here they're also encapsulating all of the underlying parameterization stuff, which is kind of put together just as fine. Okay, cool. Any more questions on this question? Or let's move forward. Okay, let's keep going. So the next one, the question was to formulate a method to interpolate between two transformation matrices. So any ideas on this one? Ben? Since you already put a PR about it?
Yeah, so you can do the box minus.
Yeah, you can write it on the board. No.
Because I want to.
Because you want to, yeah.
No eraser.
Oh, really?
You can use there's a chalkboard eraser behind you. I don't know if it works.
Probably gonna make a mess.
Is it?
Yeah, it's not so bad. Thanks, Matt. So the way I thought about it is you have like the translation portion could be handled just interpolating linearly, and then you can have two rotations. So like one rotation 1 and rotation 2 both in the same frame, and then to get the relative rotation, you can just do the box minus. And with this guy, you take the log mass of that thing, so call it and once you have it in the algebra, the magnitude of the kind of twofold form of it is the magnitude of rotation. So you can just scale that by whatever amount you want to interpolate, 0 to 1. And then, so I'll just introduce like this guy, which is going to control how much interpolation you do. And then you can get a interpolated from 1 to 2 by use of notation. And this is just going to be exponential math. That guy. And this is some kind of relative amount moving from 1 towards 2. And so then to get your final rotation, you just combine. This is more like
Yeah, no, that looks all right. All right, any questions on what Ben did? And then we'll go through, so I worked through it, well, I didn't work through it personally, but I found a resource that worked through it, and it's very similar, so we'll go through that step by step. But yeah, no, that's really good. Cool. All right, thanks, Ben. So, going along with what Ben wrote down, let's start off with, so when we consider linear interpolation, right? So the first equation is how we would normally write linear interpolation. So if you have 1 minus alpha times x1, and then 1 plus alpha x2, and then based on, if you look at the extremes, if alpha is 0, then you end up with x1, and then if alpha is 1, you end up with x2, right? So the question is, can we do something similar for SO3 or SE3, but what's the problem with something down here? So what's the problem with trying to do that? Do just straight linear interpolation of the matrices.
Addition is a group element.
Exactly. So addition, so the group element is enclosed under addition. So you can't just add. This is literally saying scale one rotation matrix or transformation matrix by an alpha, by a scalar, and try to add to another rotation matrix. But that won't necessarily be part of SO3 or SE3. So we need to come up with something slightly more fancy. So this is just saying that, yeah. So in general, this is not true. So you can't say that C1 plus C2 or T1 plus T2 is going to be an SO3 and SE3. So what we want to do is define an interpolation scheme, and we can think of it in the following way that we have written up there. So let's say C is the interpolated amount, and then we have two rotations, C2 and C1, and then what we have inside the brackets is essentially what Ben was writing as box minus, and then to the power of alpha is our interpolator, or the amount we're going to interpolate, and alpha exists between 0 and 1. So you can see here, if alpha is equal to 0, then everything on that left-hand side of C1 becomes identity, so you have a matrix to the power of 0, it's identity. Or if you have alpha to the power of 1, then we have just C2 times C1 transpose, and the C1 transpose and the C1 cancel out, and you have C2. So this is almost equivalent to what we were discussing in linear interpolation, but now we're guaranteed that these elements are actually contained within SO3 because we're just multiplying rotation matrices. And the matrix group operator, the operator for the SO3 is multiplication. So it's guaranteed to be closed under multiplication. So let's take a look closer of what this is actually doing. So, and this is what I was talking about here. So when A equals 0, we have that C equals C1, and when alpha equals 1, we have C2. Right, so let's take a closer look. So if we define now this thing that was inside the bracket, so C2 times C1 transpose, if we define that as C21, and this is what? This is just equivalent to the exponential map of some equivalent element in the Lie algebra that is small phi 2, 1 in skew symmetric form, right? So this is essentially what Ben was writing on the board, but using box minus. So you could do box minus and come up with this expression in the Lie algebra. So when we replace inside of the bracket, so C2 times C1 transpose, with this expression here for C21, we get C21 raised to the power of alpha. So because this is an exponent, we can bring it down inside of the argument. And what do we end up with? We end up with the exponential map of some scaled version of the element in the Lie algebra that moves us between rotation matrix 1 and rotation matrix 2. So this is exactly what Ben was writing on previously, just in a slightly different notation, saying that we can move alpha between 0 and 1 and essentially interpolate on the Lie algebra. And we can do this because the elements in the Lie algebra are a vector space, and then when we take the exponential map, we get back to an element in the group, in SM. Cool, so any questions on that? We're good? Everything makes sense? Okay, awesome. And then just to finish up the discussion, because we're just talking, you can do this exact same thing in SE3, either using the exponential map of the SE3 Lie algebra elements, or if you're treating the parameterization more as SO3 cross R3, then you could just do linear interpolation on the portions of R3. So there'll be equivalent representation. Cool. So any questions on that before we move forward? All right, then I'll hand it off to Jason, who's going to take us through the next piece of homework on computer vision.
I just have a quick question.
Yeah.
Maybe not, well, maybe it's a good question, I don't know. So, for linear interpolation, it's from the form clear that essentially if I double my alpha, I will just trying to think.
Yeah.
I will basically have a linear, increase in
Yeah, yeah,
my input.
okay.
Yes, right?
Yeah, I mean, it's proportional.
It's proportional, it's linear
Yeah.
proportional.
But
exactly.
it's not clear to me for the Lie algebra that this is the case. I mean, it could be something like a,
Yeah,
Yeah.
it's a nonlinear mapping through the
Yeah.
exponential map.
yeah.
So I think I've seen some proof where I can't remember the exact term that they say, but it's somehow the shortest distance between the 2 points on the Lie group. But I'll have to go back and find the proof for that. There was I recall going through that at some point.
I mean, I suppose it kind of doesn't matter in the end.
It doesn't actually, I'm not sure that but what you wrote there doesn't actually prove that you've kind of proved the endpoints,
Yeah,
but not the middle point. Like, the
yeah.
middle
There's
point
no
might- Middle point might be outside the.
right. So then we wouldn't call this linear interpolation, but it will provide some interpolation. But
It's clear.
this
it's gonna be
doesn't
clear,
guarantee
right?
the proportionality that's linear
That's
between.
right. That was pretty
Right.
much my
Right.
question.
Because it's hard to define that concept of linearity. It'll definitely be linear in the Lie algebra, but it's
Well,
unclear what that means in the Lie group
It
because
says
you're.
linear in the magnitude of rotation.
Well, that's true actually, yeah, because it is this magnitude of
Yeah,
rotation,
that's
right?
right. Prove-
Oh yeah,
prove
that's a
that-
good point. Yeah, so Ben brought up a good point because when you multiply that vector
Yeah.
by a scalar, you're essentially just changing the magnitude of rotation. So because you're changing the magnitude of rotation, you can think of it as just interpolating the rotation magnitude as well. Yeah. Yep, that makes sense. Okay, cool. All right. So any other questions before we give to Jason?
So has anyone done the computer vision homework? I think I had 2 questions. Read and summarize the surf detector and descriptor and the auto detector and descriptor. Has anyone done that or somewhat?
They were big questions.
They were big
For one-
questions
for one.
and a lot of details in that, but I'll give you a quick overview. So do you want to talk about what you know or should I just go through?
You should probably just go through.
Okay. So I'm going to describe the surf detector first. And there's a little background work that we need to understand before we go into the surf detector. And that is the concept of integral images. And so what we have over here is basically our original image, and then we sort of transform it into this whole sum area table. And what this allows us to do is quickly calculate the mean of a patch just by 4 operations over here. So the way we create this whole sum area table is we take all the pixel values that are either above or to the left of the current pixel value and add those up. So let's say we want to try and create this square over here, 24. What we would, if we start with the top left pixel, that is the same value as the original image. But as you go further on right, you sum the previous pixels to the left and above that, which means 5 plus 2 is 7, and then you go 5 plus 5 plus 2 is 12, and you keep summing that over here. At the same time, when you go down, you keep summing the same thing. So let's try and understand how we reach this value of 24, right? So if we assume that we currently have the values 16 and 12 over here from our sum table, and we have the original value 3, we basically take the values of 16 plus 12 minus 7 plus 3. And what this allows us to do is, because 16 is the sum value of this entire portion, 12 is
We
the
don't
sum.
see a pointer. Maybe you're showing
Oh, sorry, you
something,
can't
but
see a
we
pointer?
don't see anything.
Oh, sorry, my bad.
Yeah, so
Sorry, I thought it was shared screen, but clearly not. Okay, so we're trying to create the value 24 over here, right? So what we have the sum table of these values and 8 and 16. So, but what does 16 actually represent? 16 represents the sum of all the pixel values up to this point, right? So 16 is basically this over here, 16 plus 5 plus 2 plus 3. At the same time, 12 is the value of these points over here, 5 plus 2 plus 5. But the common part between 16 and 12 is this whole region over here, right? And so we're technically repeating that region twice. Is everyone with me so far? And so what we have to do is, when we're trying to get this value 24 over here, we take 16 plus 12 minus 7 and minus plus the original value 3 in order to get this value of 24 over here. This 24 value is equivalent to summing these 6 values over here. Is that clear so far? Okay, so that's how we create this whole sum table. Now once we have this whole integral image or sum area table, let's say we're trying to calculate the value, the intensity of this entire patch here in red. So this entire patch, if we had to calculate it on the original image, we would have to take 6 plus 3 plus all, basically sum up all these 9 values, right? That means we have about 8 operations over there. But with this sum area table, we can just represent it with 4 values, which is taking this value over here, right? Adding the corner value over here and subtracting these 2 values at either end. And the reason why it takes into account these operations is because 64 represents the entire sum value of the whole table. 5 represents the sum value up to this region. 14 represents the sum value of this whole area. And 16 represents the value of this whole area. So there are certain areas that are repeating twice, and if you actually work this out, you'll see that by using these simple 4 operations instead of all these operations, you arrive at the same value over here.
So is it basically just subtracting the areas of rectangles?
Yeah, it's just adding and subtracting that pixel value, right, just to get the entire area. And so what you can do is that instead of, as you take larger rectangles, the number of operations is still limited to 4 rather than actually summing all the pixel values in that particular.
So it's constant time.
So it's constant time, exactly.
Independent of the patch size.
So it's constant time, and this allows you to do some very quick analysis of, is this a dark area, is this a light area, what exactly are the pixel values contained in that area in constant time, okay? So let's move on to how the surf detector actually uses this. So if you remember from the computer vision lecture, we were very interested in taking the second derivative of the Gaussian function, right, which is the Laplacian of Gaussian, and SIFT approximated the Laplacian of Gaussian by the difference of Gaussians, right? The surf detector goes one step further and approximates the Laplacian of Gaussian by using box filters. So if you see over here, we don't have sorry, let me just find where the cursor is. So this is our Gaussian filter, and this is our second derivative in the x and y directions, right? But the problem with having these filters is that it requires you to discretize it, and there are a lot of operations that are involved in this. But what they found is that you can actually approximate these filters by using simple box filters over here. And these box filters are where the integral image really plays an important role. Because now, if you had to sum over these pixels, you just have to do 4 operations and multiply it by the corresponding weight of either +1, -2, or +1, right? And so you apply this whole Gaussian filter or box filter, discretized box filter, and you're able to calculate the intensities of that patch. Okay? So we have, from the second derivative over here, partial derivative, we approximated by box filters. And then at the same time, once we apply this patch onto the original image, we go back to the whole calculating the Hessian of the matrix and then taking the determinant to see if it is actually, and then once you calculate the determinant, you take the corner value and see if the corner value is above a certain threshold and whether it's a good point to track. Is everyone with me so far? This is all from the previous computer vision lecture. Yes? Okay, I'm going to move on. And so what originally the SIFT detector did was, originally what the SIFT detector did was, it took each image, and if you remember, it blurred it and then downsampled the image and then continued the blurring, right? But what the surf detector does is, because you can apply filters, any size filter in constant time and get the value of the filter in constant time, it tends to, instead of working on the image, it works on the filters. And by working on the filters, you can increase the size of the filter but still get the corresponding value in constant time. Right? And so this is where it's really useful, and that's why it's called the speeded up robust features, because it purely works with integral images rather than on the actual pixel values we are summing everything. Okay? So that was the surf detector. The surf descriptor again. So now that we have the key points, we know that certain points are good to track that are detected. we're actually trying to calculate the dominant orientation so that we achieve rotation invariance. And the way that's done is again similar to the SIF descriptor, where it takes the derivative in the x and y directions of a particular patch, and then it calculates the dominant orientation over here based on the window. So if I have a patch that describes the image, I calculate the x and y directions in that particular patch, and let's say these are certain values. For each of these windows over here, which is pi by 3, it calculates the dominant orientation vector.
So for the SIF detector, right? It
Yeah.
was saying the derivatives are based on the intensity differences?
Yeah.
Each pixel?
So
Okay.
here, the x and y differences. Okay. So that's how it achieves orientation invariance. So once it has, so it'll keep moving this in increments of pi by 3, and once it has its dominant orientation, it assumes that as the true north, and everything is with regard to that true north direction. Okay. And so after I get the dominant orientation over here, I analyze a certain patch around my image. I again take the gradients orientations and I sum this. The thing about the difference between the SURF descriptor and the SIFT descriptor is that the SIFT descriptor is actually a 128 dimensional descriptor. So while it has good descriptive powers, it takes a lot of time, whereas this is a 64 dimensional descriptor. And so besides taking, and so the reason why it's a 64 is because for each of these patches, right, for each of these patches over here, each of these smaller squares, which is 4 by 4, it calculates 4 values, basically the sum of the x gradients, the magnitude, and in the y directions as well. So you have a 16 into 4, which is your 64 dimensional descriptor. The other point that that distinguishes SURF from SIFT is that while calculating the Hessian or the determinant at that point, it also stores the sign, right? So if I have a white blob on a back, so by storing the sign, it's able to distinguish whether it has a white blob on a darker background or a black blob on a lighter background. And it will only compare these two descriptors if the signs of the descriptors are the same. So this is how it achieves additional speeded up feature there. So I was able to perform everything really fast. So is everyone okay with again, I urge you that there are a lot of details in SURF, just like SIFT, that you would probably have to read the paper to understand, but this is the general overview.
Okay, so when they're doing so when you come up with this descriptor,
Yeah.
how do they actually make the decisions to say, okay, we're going to take, histograms over the gradients and the magnitude of the gradients and X and Y? So what is that actually, like, how do you come up with that decision? Or is that just like how they engineer the feature descriptor? Or
That's just how they engineered the feature descriptor. So they found
Okay.
out that SIFT was performing really well as well, and so they decided to do.
so is this basically an approximation then of what
Yeah, it's an approximation of
The SIFT
SIFT.
descriptor.
Yeah, but it's faster because it works on integrated images.
Okay, and then I assume that later they did a comparison to see how well the
Yeah,
approximation was.
I haven't really gone through the comparisons, but it seems, based on what I read, I think it seems to perform as well, just in a shorter period of time. I mean, the matching and stuff.
Okay, so the gist of this is there's no reason to use SIFT if you can use SURF. Like, where would you want to use SURF rather? Like, would there be any reason why you want to use SIFT over SURF?
Would there be any reason? So I guess if you're not taking time into account,
Yeah.
right? If you're just comparing two images and want to do it, one is more accurate than the other, then there's probably a reason to use SIFT because it has a 128 dimensional descriptor, so it has a lot more descriptive power.
Okay.
But if you need sort of real time, then people have moved on to SURF, and then you've also moved on to other things. Another reason why you wouldn't want to use SIFT or SURF is because they're non-free module packets, so they're patented, right? And so every time you use it, you'd have to, well,
Have the right license.
have the right licenses. That's true. So that's why we've come up with other descriptors as well. But basically, SURF was invented to be a faster version of SIFT, is what I understood. Okay. Great. Has anyone read or done the org descriptor? Okay. Is the SURF detector descriptor understood? Yes? Somewhat.
What's going on with those patches, the image patch there? You say each patch is a 4-dimensional vector,
Right.
but
So you're just summing up the dx and dy's in those 4 patches.
Right, I don't really understand the diagram. Is that kind of expanded version?
Yeah, it's the expanded version
That's
of
a
one of the
patch.
squares. Yeah, yeah.
But then each vector is described by 2 values, right? So would-
Yeah, but the descriptor is summed over the window, right? So even though each smaller patch has a dx and dy, you're actually summing each of the dx's of those 4 smaller patches,
Oh,
right? So there are sums over here. So basically you still get 4 values over here with dx and then the absolute value of dx.
So are those smaller points pixels then? Or are those-
Sorry?
Are
Which
those
one?
smaller points pixels? Or the smaller patches of those pixels?
These over here?
Yeah.
So these patches actually contain, I think, another 5 by 5 pixels inside them.
Okay.
So there's a lot of summing going on. Again, there are a lot of details in the paper that you will probably have to read. But these are, so you take a particular point, you take a larger window around it, and you divide it into 4 smaller windows. And then you sum over those windows, and once you sum over those windows, you get 4 values, and then you concatenate all those 4 values into a larger 64-dimensional display.
Wait, so a quick question. So then does the descriptor vector for that, is it basically, does it have the sum over the different window sizes as well? So it's like you'll have, because in that picture there, right?
Yeah.
You could do a sum over the 4 big squares,
Yeah.
and then you can do the sum over the smaller 8 squares and the smaller, as you keep going down.
So what smaller 4 squares?
So see your big, that picture with the circle around it?
Yeah.
So you could divide that into 4 quadrants, right?
Right.
And then you can sum all the gradients over each quadrant, and
Yeah.
that come up with basically 4 values, right?
Right. So each of these 4 squares
Yeah.
contribute to one 4-dimensional descriptor,
Okay.
right? So you're not summing over particular 4 and then grouping 4 to form another.
Oh, so you're not grouping?
No, you're not doing that. So so I don't know why it's not showing up on the screen over here, but over here it's clearly shown that each of these patches. So this patch over
Yeah.
here, right, contributes to a 4-dimensional descriptor.
I see.
And then because you have 1, 2, 3, 4, and 4 down, you have 16 patches, and each of those 16 patches gives you a 4-dimensional descriptor, so you get 64 dimensions.
Okay.
Right? So the 4 values actually come from this square over here. Okay, so let's move on to OR, which is the Oriented, Fast, and Robust Brief Feature Detector Descriptor. And this uses the fast corner detector and, as I mentioned, the Harris corner measure. In order to get scale invariance, it detects fast at different levels in an image pyramid. And we went over the fast detector and in the previous computer vision lecture. Do people remember the fast detector? Right? Okay.
Right.
Sorry? Yeah, it's just that pixel, and you take a certain region around, calculate if the intensity in that ring is either lighter or darker than the center pixel. And if it is lighter or darker, if you have n consecutive pixels that are either lighter or darker, then the corresponding center pixel under consideration, then you have a good point to probably track or describe, right? And so that's it. So it's called the Oriented, Fast, and Robust Brief. But the problem with the fast detector was that it didn't have orientation invariance, right? And so what ORB is doing is it's adding this whole orientation factor into it. So before I get into this whole orientation aspect, let me describe, actually I should have probably, okay, so I'll come back to the descriptor, but now that we're talking about the detector and the orientation, that is calculated by calculating moments of the particular patch. Right? So once you have detected that a particular point is good by the fast corner detector and the Harris measure, now I want to calculate the dominant orientation of that particular patch. And the way that is calculated is by using moments of the image. So you have this formula over here that describes the patch, the patch moments, right? And so if you're considering a particular point and a patch around that point, it is not necessary that the centroid of that patch is the actual point under consideration. And what I mean by that is, that if by chance I'm analyzing if O is the point that my fast detector returned, right? C could be the point where the center of mass of that particular patch is actually located. And the center of mass is calculated by using these image moments, right? So the center of mass is given by M10, and the way you calculate this M10 is by the formula above. So M10 would be basically your Y would go away, and you just calculate your X times the intensity of your X and Y, and times the intensity of that particular pixel, sum over the entire window. Right? Okay. So by calculating these image moments over your M1001, you can now get the centroid of the particular patch. So let's assume that this was the patch under consideration. O was the point that the fast detector returned. By calculating these values, we reach a point C. Now we can calculate the vector that goes, the angle of the vector that goes from C to O with the horizontal. And by calculating this angle and storing this angle, we now get the dominant orientation of that particular patch. Okay? So you take theta over here and you get this value. Is it clear how we get the dominant orientation with regard to this detector? Are the details a little hazy, or yes? Okay, I'm going back. Okay, so now we know that the fast detector returns a corner. We know that by calculating the image moments, we get the dominant orientation, right? Okay, so I'll come back to, so that is the orb detector. I'll come back to the orb descriptor. But the orb descriptor basically uses the brief descriptor with a certain chain. So I'll have to probably describe what the brief descriptor is. Well, the brief descriptor is a binary, robust, independent elementary features. And what this means is that once I have detected a point of interest over here, I take a patch around this point that is under consideration. And what brief does is it randomly selected different comparisons. So what it would do is it would take, let's say, a value, the pixel intensity value over here, and the corresponding endpoint of that particular line, and see if this pixel value is either lighter or darker. If a pixel value is either lighter or darker, it will assign a 1 to it. If let's say I have pixel P1 which is at one end and pixel P2 which is at the other end. If P1 is lighter than P2, if the intensity of P1 is lighter than P2, it would assign a 0. Or if P1 is if the intensity of P1 is greater than the intensity of P2, then it would assign a 1 to it. And by assigning this 1 and zeros, you now get a binary descriptor. So a descriptor which is just basically ones and zeros, right? And so by randomly selecting intensity values, it comes up with either 128 or 256 or 512 dimensional descriptors. And because this descriptor is binary, which means it either consists of either ones or zeros, the way to compare this is by using the Hamming distance or XOR, right? So how many bits correspond to each other. And based on that value, we see whether the two descriptors match, and hence the 2 points match if you've detected the same point. Right? So if you have a descriptor which is 1010 and 0101, they're probably not going to match.
But this is after the orientation is aligned.
So this is the brief descriptor. Yeah. So this is after the orientation is aligned. So you use the fast, you get the dominant orientation. Now you use, this is the brief, but the orb goes one step further and saying that instead of just randomly choosing pixel comparisons, what can we actually learn which pixel comparisons work the best, right? And so the way orb does it was it learned to detect which comparisons to use. And there's a whole method on how they actually learn which pixel comparisons to use, and I can probably get into that, but I don't know. Do we have time?
So
Okay.
is there like a machine learning component to it?
There is I guess there is a machine learning component to it, but It's a very
Wow, like it has to be really light in order for it to work
Sorry?
so fast. It has to be really light, right?
What's the certainty going through?
Yeah, they already.
Maybe
No,
training.
no, no. So the training was done offline, right?
Alright.
And they once the training was done offline and they determined which comparisons to use, which pixel comparisons to use,
Yeah.
then they just used that set of pixel comparisons, right?
But then isn't the selection of the set of comparisons then biased towards whatever training data? used?
Exactly. Yes.
So then if you trained it all on like for matching buildings outside,
Yeah.
or indoors, for example,
Right.
and then you take it outdoors,
Right.
then
Yes,
is there-
but when they came up with that, they wouldn't bias it towards particular.
right.
So yeah, it's very dependent on what training data they used, and the training data that they actually used was they used 3,000 key points. So they used 3,000 tests from images obtained in the Pascal data set.
What's the best one? Is it?
So
Just like image.
it's a data set, image database, basically.
Oh, okay.
Yeah.
But it's just a bunch of different pictures.
It's a bunch of
depending
different
on
pictures.
everything.
Yeah, I don't really know what categories were in the Pascal data set, but yeah.
Okay.
Random.
So,
But then also by that logic then, could you tune the orb to work really well for one domain? So if we just wanted to use it for autonomous driving, we retrain it just on training data that you get from, say, driving through a road or something?
right, so when you're saying can we train it, we're trying to find out which pixel comparisons to use. So yes,
Yeah.
you could develop your own thing, right? It's just a modified version of brief.
Yeah,
It's
instead of
just-
random, it's.
Yeah, it's just saying instead of randomly choosing values. And so if you look, there's besides brief, there's also brisk and there's free, which say that now that I have this pixel point, I don't know if you all remember from the last lecture, I divide it into circles. And so what Freak would do was it'll take a lot of comparisons closer to the actual, so it will take a lot of comparisons that are closer around the pixel under consideration
Yes.
than ones that are further away, right? But what Brief is doing is you can see all the comparisons are evenly spread out.
Yeah. So then, do they ever compare to like the brute force, where the comparisons are basically every pixel at every pixels, like n squared number of pixels? Because this is basically just trying to speed up whatever pixels you're selecting against, right?
Yeah.
Comparing against. But would you then get the best performance if you were to just do brute force comparison?
When you say brute force comparison, you're talking about measuring descriptors, where the two descriptors are the same?
No, so here it's doing pixel comparisons between
Yeah.
random pairs, right?
Yeah.
So what if you did a comparison for each pixel to every other pixel? So it's fully,
Right.
fully connected. type of-
Right, but then you're talking about that running in real time?
No, just as a baseline comparison.
As a baseline, yeah, I'm sure they must have done that, but I don't really know.
Okay.
So we could probably go through the learning component of how they did this, or we could skip it.
So, okay, interesting question.
Yeah.
So far
Of
you've
course.
discussed a couple of descriptors of that trying to be scale and orientation variant.
Yeah.
But let's say, for example, if I have a VIO, of course I'm going to talk about VIO, and I have like a 120 FPS counter, would it actually make any difference, like frame by frame? Like the time difference is so small.
Mhm.
Would the orientation actually make any difference? Like the robustness. Like, do I actually need robust descriptors for rotation?
Do you need robust responses?
Yeah, if my FPS is so high, is that like a analysis to say,
Well,
Okay. Alright, so let's, this class is being used at 7 o'clock, unfortunately, because of the time shift. So
This is a Monday schedule now. Today.
It's a Monday schedule. I confirmed, I asked.
Yeah,
the,
but your lecture is on Monday.
but not at this time. Our Monday lecture is really.
Oh, that's right.
Yeah, I asked the undergrad office. The undergrad office. But anyways, if we can bring the discussion back to that. Yeah.
Yeah.